Unit 2, pages 22 to 27, the periodic table. All of the known elements are arranged by atomic number in the periodic table. Much of the chemistry of an element can be determined by its location on the table. Periods are horizontal across the periodic table, and groups are vertical. Elements in the columns or groups have similar chemical properties, and periods are elements arranged in the rows of the table. Notice the location of the main group elements. They're going to be the first two columns, tall columns on the left, and the last 6 tall columns on the far right. And they're going to make up our 8 main groups. Then we have the transition metals, and down here are the intertransition metals. Metals, nonmetals, and metalloids. You should know the location of these types of elements. Note that hydrogen is not considered a metal, though it is found on the left side of the periodic table where the metals are located. So here are all your metals. Here are your nonmetals, and then these are specifically the metalloids. Properties of metals: they conduct electricity and heat, they are shiny or have high luster, they are bendable, malleable, and ductile, and they like to lose electrons when forming ions, which means they're going to form into positive cations. Properties of nonmetals: they're brittle, many are gases or powders, they don't conduct heat or electricity, and they like to gain electrons to form anions. Properties of metalloids: these elements have properties that are in between the metals and nonmetals. They partially conduct heat and electricity, can be shiny but are usually brittle, and are semiconductors for electronics like computer chips based on these materials. Information in the periodic table. The box for each element in the table contains the following useful information: the elemental symbol, its atomic number, and its average mass, AMU, per atom or grams per mole. The average mass is used because elements as they are found in nature usually consist of many isotopes with different masses. As a common mistake, students often confuse average mass with mass number. Mass number is always an integer because it represents the number of protons and neutrons. The actual mass of the isotope is not an integer. The average mass is the average of all isotopes. Example 2.9. Naturally occurring magnesium consists of almost entirely of 3 isotopes. Use the isotopic information provided in this chart and calculate the mass of magnesium 26, which is this one. We don't know its atomic mass units. So remember that the equation is average mass is equal to the sum of the mass times abundance. And what we don't know here is one of the masses. So we need to locate the average mass, which you can find on the periodic table for magnesium, which happens to be 24.305, equals the mass of magnesium 24 is 23.98504 times its abundance 0.7870 plus the abundance of number 25, 24.98584 times 0.1013, and we'll add that to 0.1117x because we don't know what this mass is. So it's this times this, and this is what we don't know. So we're going to solve this for x, and first you want to simplify. Multiply these two values to one another and these two values to one another, and we're going to get the average mass is equal to 18.876226648 plus 2.5310655592. And then we still have plus 0.1117x. Then we're going to subtract or combine these two values, and that's going to give us 21.40729.207. We'll subtract this from both sides of the equation, which is going to leave us with 2.897707928 equals 0.1117x, and then I'll divide both sides by this value, which is going to get me x is equal to 25.94187.939. And so essentially my atomic mass units for magnesium 26 is 25.9419. I'm going to show you how you can calculate this all in your calculator with 2 easy steps. I'm going to type in this value, 24.305, because my x is over here. And I know that I'm going to end up subtracting this to the other side as well as this. So I'm going to hit minus, open parenthesis, 23.98504 times 0.7870, close parenthesis. And I'm going to subtract this set, so minus open parenthesis 24.98584 times 0.1013 close parenthesis. I'm going to go ahead and hit equals, and that's going to be this number minus this. And that gives me this value, and all I have left to do now is divide both sides by the 0.1117, and that gets me my x, which is 25.9418. Naturally occurring boron consists of two isotopes. When you think about the atoms in a sample of boron, you should picture two different types of boron atoms. The mass listed in the periodic table for boron is its average mass of the two isotopes in the sample. So if we look here at this diagram, we have two different borons, boron 10 and boron 11. Boron 10 has a mass of 10.013 atomic mass units at 18.8%, while boron 11 is 11.009 atomic mass units at 81.2%. So the average mass from the periodic table is going to be equal to these multiplied to one another plus these multiplied to one another, which gives you 10.82 atomic mass units. However, if you were to know that this was the percentage of boron 10 and this was the percentage of boron 11, then you should be able to look at a diagram like this and note that it has a total of 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 total species present. And so 2 of those 10 would have to be boron 10 in order to meet this 18.8%, and 8 of the 10 would have to be boron 11 in order to be close to this 80%. So you'll be seeing a lot of these diagrams in the practice sets. Here's your note card for this section. First of all, average mass is always found on the periodic table. Don't get it confused with mass number. When metals lose electrons, they form cations. Nonmetals will gain electrons and form anions. And then consider this sample set of isotopes. You have an element with a mass of 13, element with a mass of 14, and one with a mass of 15. Notice we have a total of 3, 6, 9 in this segment, and there's 5 out of 9 that have a mass of 13, 3 out of 9 with a mass of 14, 1 out of 9 with a mass of 15. So the mass of 13 makes up approximately 55%, while mass of 14, 33%, mass of 15, 11%, and notice that altogether that's roughly 99 to 100% of your little box there. So this is how we can use this to take a sampling and determine the relative abundance of each mass that is present here. And if I wanted to know the average mass of all of these here, then I would say 13 times 0.55 plus 14 times 0.33 plus 15 times 0.11, and I would get the average mass, and it should be closer to mass of 13 since it's the most abundant isotope.